back to the iron-carbon phase diagram. All right. So we had mentioned on Wednesday there's a whole bunch of reactions, but the one that we're really concerned about is this eutectoid point. And in fact, my sort of ad hoc definition of steel said there's alloys of iron that are descendants of this eutectoid reaction, right? And essentially, if we're at low enough carbon content, under 2%, we're going to come down through, and we're going to decompose, depending on where exactly we are, to some mixture of ferrite and cementite, or ferrite and graphite. And the cementite's not the thermodynamically stable compound, but it is highly metastable. And so most of the time we're going to be talking about the eutectoid. There's a couple other reactions, right? There's this paratectic point way up here, and then the eutectic. The eutectic doesn't matter to us, right? Because that's at 4.3 weight percent iron, right? Well beyond anything that we're interested in. This is out in cast iron territory. The paratectic reaction, so here's the paratectic point where we have a mixture of liquid and delta, which is going to spontaneously react and transform to austenite if you're at the paratectic point. And this transformation only has secondary effects. Remember, a paratectic is kind of like a eutectic turned upside down, right? Instead of having one phase spontaneously decompose, right, now you have two that react to form one. Right? There's only secondary effects of this, because anything that's going to go near this paratectic point also is going to come into the full austenite phase regime, right? And provided that you're cooling slowly, you're going to have time to, and it's a high enough temperature, you're going to have time to equilibrate. You may have, depending on the cooling rate, some coring effects or segregation. All right, but for the most part, we can ignore this, and delta iron doesn't have any strong effect on the overall structure and properties of our final steel product. All right, so if we're less than 2.11 weight percent, right? Just remember, everything that I'm talking about is weight percent, not atomic percent. Right. Right. 2.11 atomic percent is not a whole lot, right? Being the density difference between carbon or the atomic mass difference between iron and carbon. So generally, if we're between 0 and 2.11%, this interval is arbitrarily classified as, I would say, carbon steels, right? But right, most carbon steels, though, have carbon content of less than 1%. 0.2 to 0.3% carbon are our building and construction steels and account for most of the tonnage. There are tool steels which can have significantly high quality steels, which used to be sometimes classified as Sheffield steels due to the knife making industry in Sheffield, England, or Solingen steels from Germany. These are high carbon tool steels and can be 1.2, 1.3%. Anything above 2 is sort of arbitrarily classified as a cast iron. But in reality, cast irons contain Lots of silicon in there and some other elements. Really, cast irons, when we'll look at them at the end, and we'll have a lecture at the end of the semester. Really, we're better off considering those as ternary alloys of iron, carbon, and silicon, because the silicon promotes the formation of graphite more easily rather than cementite. Right? And the cast irons tend to be much more easier to machine than steels because the graphite makes them self-lubricating. Right? You don't need to use any cutting fluid when you're machining cast iron because the graphite handles that for you. And again, for steels, we're really going to be mostly concerned with lots of compositions near the eutectic point. Right? At the lower carbon steels, not much is done to them. Right? They're just used in they're hypo eutectic, so they're just ferrite pearlitic steels, and there's not a whole lot of interesting things technologically going on with them. So we're going to be, again, mainly concerned with things near the eutectic point, right? And of course, being that this is a physical metallurgy class, we should really know that the microstructure, if we consider slowly cooling from the austenitic region, is going to depend strongly on the carbon concentration of the steel, right? So if we are above the eutectic point, we're going to have, or below the eutectic point, hypoeutectoid, right? We're going to have proeutectoid ferrite and then pearlite. And if we're above, we're going to have only pearlite. If it's higher, we're going to have proeutectoid cementite, right? So just a look at the micrographs, the microstructure of hypo and hypereutectoid steels, right? So as we come down, what formed first? Right? We've got this hypoeutectoid ferrite that grew as we came down through the two-phase region, right? We had ferrite plus liquid, then we came down into the other region, and then the pearlite grows. If we're hypereutectoid, we have liquid plus cementite, or not liquid. Why didn't anyone correct me? It's the eutectoid reaction, not the eutectic. The eutectoid, we're going from alpha to ferrite and austenite and ferrite to ferrite plus cementite, right? So we come down, we grow the ferrite, we have all austenite, we nucleate and grow ferrite, then once we cross, we transform the remaining austenite into ferrite and pearlite, right? If we're hypereutectoid, we're austenite. As we come down, we cross into the austenite plus cementite, and we grow cementite on the grain boundaries. And then we grow ferrite and cementite in the form of pearlite, right? And we'll talk about, all of next lecture will be about the growth of pearlite, right? So, but right now we're talking about the growth of ferrite, and we have a couple different mechanisms that we need to consider, right? We have reconstructive or diffusive based, and then displacive or shear based. So someone asked me a question about why the shear, right? And the answer is the mechanisms of these are all fairly complicated at the atomistic scale. But the important thing, remember, is there are volume differences, right? The size of the unit cell of the austenite and the ferrite are not exactly the same, right? So if you have a purely diffusive transformation, it's not that bad, right? Because the atoms are jumping and rearranging, right? And you're diffusing carbon. You're diffusing carbon out, and that's fine, but it takes time. If you're going a little faster, the end spectrum of that is martensite, right? Where you don't have time to diffuse anything away, and you have a large shear going from austenite to body center to trigonal. In between, we have bainite and this Widmanstatten ferrite, where we have a invariant shear coupled with diffusion at the same time, right? Where the carbon is moving as the shear transformation takes place. Right? It should be obvious to everybody that shearing also is one way of accommodating a volume change, right? We're not when going from one crystal structure to the other, we don't necessarily have to. We don't have the same volume. It'll be a little clearer when we talk about the martensite reaction in detail. And I want to bring this notion of para-equilibrium back up. All the mechanisms that we're going to be talking about assume that they happen at a scale where carbon redistributes, but the substitutional solutes move too slowly for full equilibrium, right? So they are only going to diffuse sort of after the transformation takes place. Okay. So both of the pro-eutectoid ferrite and pro-eutectoid cementite that we showed there nucleate preferentially and heterogeneously on the prior austenite grain boundaries. Right? Grain boundaries facilitate higher diffusion rates, right? By grain boundary diffusion. So when ferrite nucleates at an austenite grain boundary, there's typically an orientation relationship that develops. And this is a very important orientation relationship, and the only orientation relationship I will ever ask you to memorize. And this is the Kurdyumov-Sachs relationship between FCC and BCC. And what we have here is in austenite, the 111 plane, the close packed plane, right, is parallel with a 110 type plane in BCC. So it's the close packed FCC plane and a plane that contains the close packed direction in BCC. And then the 101 type direction in austenite parallel with the 111 direction in austenite, right? And this is equivalent to a 90-degree rotation about a 211 type plane. So that's how they stack together. And one of the questions to ponder is to play with this relationship. Right? And this is an exceptionally low energy interface. And it comes up in more than just steel. If you take copper and niobium, copper is FCC, niobium is BCC, there's a technique called accumulative roll bonding, where you basically put two sheets on top of each other, roll them, cut them, and keep stacking them up, and keep rolling, and you can get rolling strains of several hundred times in there, so that the original plates now become nanometer thin layers, and you can make nanocomposites of aluminum and of FCC and BCC metals just by rolling. And guess what guess what relationship all those grain boundaries end up taking? Right, that's Kirchhoff sacks. Right, you end up with layers of extremely low energy interfaces that develop through this purely mechanical process. Right, so it comes up again and again, and this is a very low angle boundary because it's, low energy boundary. Right, so because this habit plane is low energy, it doesn't move during the growth, right? So we nucleate with this orientation relationship. Then we're going to grow our nucleus. Well, one side's going to keep that Kirchhoff-Sachs relationship, and the other side's going to grow. So when we grow our ferrite, it doesn't grow uniformly from both sides into both austenite grains, right? We start on the grain boundary. It's going to keep a preferential relationship with one of the two grains and nucleate and grow into the other grain. Right? So the ferrite, right, the boundary that's growing is going to be a general high angle or non-coherent boundary. The other side is going to be this preferential Kirchhoff-Sachs. Okay. So I mentioned two forms. I always get nervous when I try and say allotriomorphic, allotriomorph. Right? There's just so many wrong ways to say it. So I always say allotriomorphs, but I know people that say allotriomorphic. I don't know. It's important in titanium as well when you have alpha allotriomorphs that form on the beta grains, right? If you were at the seminar, Babu mentioned that very briefly. But so allotriomorphic ferrite grows on the grain boundary, and so therefore it has a shape which reflects the prior austenite grain. It doesn't have a shape that's crystallographically related. Right? So if you look at a little chunk of it, it doesn't look like a little crystal. Right? Whereas idomorphic ferrite nucleates heterogeneously at a non-metallic inclusion or intermetallic in the center of the grain, and it takes on a faceted shape. Right? There's no contact with the austenite grain surfaces, right? So it's free to make these faceted lower energy grain boundary structures, and it has a tends to be a crystallographic relationship with the, right? Its shape, when I say reflects the symmetry of the crystal embedded in the austenite, in the same way that geological crystals, when they grow, like if you ever see a quartz crystal grow, it grows this long hexagonal rhombohedral looking pointy thing. I don't even know the words to describe that exact shape. But those facets all represent important crystallographic planes in the quartz unit cell, right? And depending on where you are, quartz can either be hexagonal or trigonal. This is the same way. If you were to dig one of these out, it would look like one of those. It would look like a quartz crystal, but it wouldn't be that same shape. It would be a shape 4 BCC, right? So it looked more like bismuth crystals, those wonky things, right? Just some micrographs, right? So we see allotriomorphic ferrite is always at the grain boundaries, idomorphic ferrite inside. Both of these allotriomorphs. Damn it. You know how many times I look at these? All right. These are both true diffusional transformations. Right? That means that at an atomistic level, there isn't a correspondence between the parent and the product crystals. Right? There's no invariant plane shape change is another way of saying that, like there is for martensite or Widmanstatten or Widmanstatten ferrite or bainite, right? These are truly diffusional, right? With the exception of the Kurdyumov-Sachs habit plane, that one low energy interface. The growth rate can be either diffusion controlled or interface controlled or mixed, right? And we have to have a thermal activation necessary. We have to jump across, and because we have to have mobility, these tend to happen at higher homologous temperatures, right? If we cool slowly, we get these structures. If we cool quickly, we don't have time for the diffusive transformation to occur, and we have a shear-driven transformation or a reconstructive transformation, okay? Which means that this alpha-gamma interface doesn't need to be glissile. It doesn't need to have mobility, right? Because the interface can just stay there, and atoms can jump onto it, and it can move that way. It doesn't have to move like grain boundary motion, right? Okay, so a couple things we have to keep in mind. I promise this is like the last of the wordy slides. Right? The ferrite has a different chemical composition from the austenite in which it grows. Okay? So let's assume that we're completely diffusion controlled. Right? So the growth of the ferrite is controlled by the diffusion of the carbon in the austenite ahead of the interface. Right? So we've got an interface that's moving, low carbon, high carbon here. So what are we going to do? We're going to pile up carbon on this side, right? Because the carbon has to diffuse essentially out of the way so that carbon can grow. As the ferrite grows, the extent of this diffusion field also grows longer. So this is going to, the more it grows, it's going to slow the growth rate and retard the growth because the solute then has to diffuse over larger and larger differences, right? So this is the physical, this is sort of like the schematic picture for this, the parabolic growth rate where we have the thickness increases with the square root of time, right? And the key idea here is that the growth rate is going to slow down as the time increases. So you've probably gone through this in the phase transformations class, right? So I'm not going to go through the complete derivation, but this is sort of the general picture here, right? This is our ferrite. Here's our austenite. This is our equilibrium concentration, right? Of course, the overall we're going to decompose into ferrite and pearlite here, right? This interface is moving. The ferrite has a lower carbon concentration than the average, right? So this is the excess that continually has to keep diffusing away in front of this growing interface in order for it to happen, right? And we can write up the differential equations here for just our conservation of mass, right? Solve the PDE, and it's not that hard to do, but we get the z star distance is the square root, is going to be proportional to the square root of the diffusivity times the time, and the rate at which this grows is proportional to the diffusivity divided by the square root of the diffusivity times the time. So as this goes on, as time gets higher, we see that the growth rate is going to slow down, right? Because we've got this big pile-up effect. All right, pile up in the carbon sense, not dislocation, right? However, if the carbon content is low enough and the alloy is cooled quickly enough to avoid partitioning, but slowly enough to avoid martensite, we can have a massive transformation, right? So a massive transformation is diffusional transformation where we don't have a change in composition, right? Clearly, if the carbon content is too high, we won't be able to do that, right? So this only is going to depend on short-range diffusion, right? And because it only depends on short-range diffusion, this is faster, right? You don't need to worry about diffusing excess carbon out of the way. Our ferrite grains can grow to be much larger than the original austenite grains, right? And this tends to give us a large-grained, equiaxed ferrite microstructure. Right? So these are both in ultra-low carbon steels, right? Quenched. This one was quenched into ice from 1000 C, quenched into an ice brine. And you can see the large equiax grains. Right? And this is just, everything just needs to make a single atomic jump across the interface for the transformation to occur. Right? So it's going to be exactly proportional to the diffusivity, the mobility. Not the square root of d, t, just the diffusivity times t. Okay. And then we have to move over and consider the first of our displacement transformations, which is Widmanstatten Ferrite, which is just so much fun to say. Unlike the French names, I like the German names. I know how to say those. Right, so we have carbon diffusion during this para-equilibrium nucleation, and growth, and everyone's seen this classic Widmanstatten plates. Right, this is from EBSD image to show that the orientation of all these plates is relatively the same. Right, there is not a big, these aren't like sort of individual grains. It's not a colony like titanium where it was shown today. All of these are different shear variants, and the shears are fairly small, and so we end up with a structure that's relatively the same crystal orientation across this, even though just looking at it optically, you wouldn't necessarily assume that, right? It looks like these are a whole bunch of tiny little grains, right? So when we have new phase, it grows inward from the interface, right? These long, thin plates or needles, and this is what we call our Widmanstatten structure, right? And there can be either primary Widmanstatten, which nucleates and grows directly on the austenite grain surface, and then secondary Widmanstatten that grows from any allotriomorphic ferrite that's present. Right? So this is a plane strain deformation. We have a shear. Right? We don't. This happens faster than we can completely diffuse. They're on the same kind of time scale. And so we have a plane strain deformation, right? And we can think, if you think about this being a grain boundary, and we have a shear associated with this transformation, this is a big step, right? This would have to be accommodated by the neighboring grain, right? How do you do that, right? Imagine taking a stack of playing cards and then jogging it offset, right? And then trying to put it back into the shape, the box that it came out of, right? You'd have to tear the box, right? So there's a huge elastic energy penalty that comes with this, right? And the wider the plate, the greater this shear step is, right, because it has a characteristic shear per atomic layer. And so there's multiple different variants that can form. So essentially, you end up with layers where they have shears in opposite sense. So you only have a tiny little bump that needs to be accommodated rather than this whole big thing. So you end up with two variants that grow together into this, separated by a small misorientation between the two. Right. So this happens at low undercoolings, right? The carbon does redistribute during growth. So this is all happening during a para-equilibrium condition, right? So we still have diffusion at the of carbon ahead of the austenite plate tip. Right? So for the plates, if we're growing this way, we got a neat plate growing this way, the tip is always advancing into fresh austenite. We diffuse carbon out the side. So we can grow as long as we want, right? This growth can continue at a constant rate because we can easily partition out the side, but we're not going to partition any of the substitutional atoms, right? So I see you're going to ask a question. I'm going to get to that on the next slide. I promise. Right? So they're going to grow in length and thickness, right? So we have two different length directions. So that means we have two different types of boundary, right? We have the parallel sides of the lath and the edges of the end of the lath, right? So the sides of these laths are low energy semi-coherent boundaries and are fairly immobile and have a 558 habit plane. The end of the lath is a non-coherent high energy boundary and has really easy mobility. Right? And so on this, you expect there a strong anisotropy between lengthening of the lath versus thickening of the lath. Right? But we do have thickening because the laths grow by this lateral motion of edges or steps, right? So they grow much slower. So what we have is regions of a coherent low energy plane separated by a general high energy step, right? And these high energy steps have mobility, have significant mobility. And so they can grow this way. No problem. This step can grow this way, this one can go this way, this one can grow, this one can grow, this one can grow, this one can grow, at the same time that this tip is extending in, right? And so you maintain, right? What we don't get is growth of this low energy boundary this way, right? As we grow this step back, we're creating new low energy interface as we grow. Does that make sense? I'm getting multiple different versions of head bobs. I still haven't, despite all of my Indian colleagues and students, I still have not learned to interpret them all. I sort of envision that this is a cause of many regional conflicts on the subcontinent at some point in time. So, okay, so did I answer that? Was that what you were going to ask? Okay. I thought so. Okay. So if we look at this, if we look at the rate at which it grows as a function of the tip radius, right, we see that very thin plates have a very fast rate, and then as they get wider, it slows down. And this is due to the need for carbon to diffuse, right? If we have a wider plate, we need to diffuse more carbon, right? If we have a very sharp needle that can grow quickly, right, we don't need to move as much carbon out for the tip to lengthen. For thickening, on the other hand, these are results for in situ thickness, and this is in microns, right? And what you can see is that you get a plateau, and then a jump, and then another plateau, and a jump, and that's as these individual these layers, these ledges, they're not individual atomic layers, but they're very thin layers, essentially zip by, right? So you get this stepwise growth that happens, right? And this is not, again, you're not unique to this, right? Deformation twins, right, grow in the same way, right? They're dislocation mediated, right? So twins grow as dislocations come by, right? This ledge migration growth mechanism appears again and again and again in material science, right? It's a way that we can keep a low energy interface which doesn't have a lot of mobility, and particles can grow. Okay? So just again, Widmanstatten involves these invariant plane strain, right? We have these thin wedged plates and para-equilibrium mechanism. Okay, so we're almost done with what I wanted to get through today. Right, and this is just looking at the CCT, or the continuous cooling curves, for schematic CCT-like curves for different hypothetical alloys, right? And so if we cool down slowly, right, we have equilibrium growth of ferrite, right? Either starting from allotriomorphic or idomorphic ferrite that grows into full ferrite grains, right? So here's the nose of our transformation curve, right? If we cool a little faster and we come in sort of at the nose, we get a Widmanstatten type reaction. Alloys that could undergo a massive transformation have noses of the TTT curve that come out much farther and have a flatter top to them. We'll talk about the shapes of these curves more in steel. Is everyone comfortable with interpreting this? Right? Is anyone looking at this? Be honest. Is anyone looking at this curve and not understanding what you're looking at? Is everyone? I'm seeing some confused faces out there, but no one's raising their hand. Right? So this is the temperature, and this is the time. So if we cool at a given rate, and we make a plot of trace of temperature versus time, right? This is just following at a given time it's this temperature, given time it's this temperature, given time it's this temperature. Right? This is just a temperature trace. And then here, we say if we follow this curve down, at this time and at this temperature, we start to nucleate ferrite. At this time and this temperature, our transformation's 50% complete. Right? Then typically you would have a 99% curve line. And these make these big C's, and we call this tip the nose. So it's a good way of looking at what's happening, right? If I can cool it fast enough, I can miss the nose of this curve and avoid growing equiaxed ferrite, right? If I cool a little faster, if I come in this region, I grow Widmanstatten ferrite. Alloys with a lower carbon concentration tend to have much flatter tops to this curve, so that no matter what it all starts at about the same temperature, no matter how long you take to get there, right? Right? So if you really have transformation that happens without any diffusion, this corresponds to the tie line on your phase diagram, right? Right? This is the temperature at which you cross from one phase to the other. Right? We get massive ferrite. If we cool down fast and we miss the nose of this completely, we could get perhaps, depending on where we come in, we could get some bainite. But we get martensite, right? And martensite is a thermal transformation, right? Meaning we don't care about the temperature, or we don't care about the rate. It's all about the martensite start and the martensite finish temperature, and we'll talk about that in great detail, right? But these are for the highest quench rates, right? You don't always need to be fast to get martensite. Some alloys, 4340, for example, transforms to martensite on an air cool, right? But you'd have to cool it really slow up here, right? And believe it or not, we have samples, essentially steel samples, that are completely equilibrium compositional wise because we've had exceptionally slow cooling rates. Anyone have any idea where those came from? How they were made? So if you think about a equilibrium cooling, right, you need to hold it essentially at the transformation temperature for as long as it took for it to happen completely reversibly thermodynamically with no undercooling, right? And there's only one experiment, or one set of experiments, or maybe not even a set. There's only one place that I know of where that can actually happen, and you had your hand up. Meteorites, right? Iron, nickel, and iron carbon meteorites, right? You have exactly equilibrium, because the cooling rates in the vacuum of space, where you only have radiative cooling, right? You can take millions of years to cool down. And so we have exactly equilibrium, perfect diffusion examples of all of these. Right? So this is just essentially an example of the same thing. So ferrite, perlite up here, Widmanstatten ferrite, bainite, and then martensite down here. And this is just the morphology of the different phases. So on Monday, I will be open for questions about the exam. Oh, I got an email about answers for the questions to ponder. I want you guys to get together for those, right? Because it's been my experience, if I just give out the answers to the question to ponder, no one spends any time working on them or thinking about them. So come together, work on them together and talk, and then ask me questions on Monday or Ben questions on Tuesday, right? Or send me an email. I'm happy to email. And I'm happy to answer any questions by email as long as it's not 10:30 on Tuesday night or 3 o'clock in the afternoon Wednesday.